Hess's Law Part 2, looking at heats of formation and bond energies. We can calculate heat of reaction from the molar enthalpy of formation by Hess's law. This will always refer to a specific reaction. We will not be looking at combination from compounds or from elements outside of their standard state. This looks only at the combination of the compounds from elements in standard state. The heat of reaction will equal the sum of the heats of formation of the products multiplied by their coefficients minus the sum of the heats of formation of the reactants multiplied by their coefficients, such that the overall heat of reaction is a summation of the coefficient times the heat of formation for the product minus the sum of the coefficient times the heat of formation for the reactant. Heat of reaction is a state function, so the pathway that we take to get to the heat of reaction is irrelevant. The equation will presume that the reactants completely break down and then form products, such that all of the compounds decompose into component elements by breaking apart into all of their atoms, and then those atoms all rearrange to form products, so that there are no bonds that are left over from the breaking down of reactant to product and then making products. So we have a complete disassociation of all the atoms during the course of the reaction. Normally this is not the case that a reaction takes. Usually pieces of the molecule are conserved in a reaction. However, the same energy value will be arrived at either way. So we can use this process in order to accomplish our goal. In order for this to work, elements must be looked at in their standard state. As an example, we can calculate for the following reaction at 298 Kelvin. Using this equation, once again, if I have silicon tetrahydride plus oxygen, both in gas form, yielding silicon dioxide in solid form, plus 2 water in liquid form. They have respective molar enthalpies of formation of 34.3 kilojoules per mole reaction, 0 kilojoules per mole reaction, negative 910 kilojoules per mole reaction, and negative 285.8 kilojoules per mole reaction. This is because an element is always a 0 molar enthalpy of formation, since elements exist naturally. They're not being formed from component subatomic particles or things, according to our chemical equations. Overall, the heat of reaction then is the heat of formation of the silicon dioxide plus the heat of formation of the water times 2. From this, we would subtract the heat of formation of the silicon tetrahydride plus the heat of formation of the oxygen. If we look at the reaction then, that's negative 910.9 kilojoules per mole plus 2 times negative 285.8 kilojoules per mole, subtracting from that 34.3 kilojoules per mole plus 2 times 0, which gives us an overall heat of reaction of negative 1516.8 or 1516.8 kilojoules per mole reaction. Now, bond energies are an important thing to consider when we're looking at energetics of reactions. A chemical bond has energy to it. Any sort of chemical reaction involves the breaking and forming of chemical bonds. If I break a bond, the process will always be endothermic because we have to input energy into that chemical bond in order for it to break. Any sort of formation of a bond will be exothermic. A substance will not form a bond if it doesn't get that substance to a lower energy state, because all substances want to go to the lowest energy possible configuration. And so the only reason that an atom will bond is in order to achieve the lowest possible energy configuration. Without a decrease in energy from the bond formation, the atom wouldn't make the bond. So any bond formation process releases energy and is therefore an exothermic process. Bond energy is then defined as the amount of energy that is needed to convert 1 mole of bonds in their gas form to atoms in their gas form at constant temperature and pressure. For example, a hydrogen molecule in its gas form going to 2 hydrogen atoms in their gas form on a mole scale would have a molar heat of reaction of positive 436 kilojoules per mole of HH bonds. The higher the bond energy, the more stable the bond overall. A triple bond will be the most stable and therefore have the highest bonding energy, followed by a double bond and then a single bond. The reason for this is that pi overlap causes a greater degree of bonding between the atoms, which gives them stronger bonds. and therefore overall higher bond energies. A triple bond has two overlapping pi orbitals, or p orbitals. A double bond has only one, so it's less than a triple bond. But a single bond has none, so it will be the weakest of the three. All bonding energies that we see, for instance the positive 436 kilojoules per mole for the HH bonds, are averages of that type of bond. For example, a carbon-hydrogen bond is going to be represented as the average for all carbon-hydrogen bonds. A CH4 carbon-hydrogen bond may be different from a C2H6 carbon-hydrogen bond. However, despite using the averages, they tend to be close enough to the actual value for us to use them relatively effectively. If we look at this reaction, where we take hydrogen and bromine to make 2HBr, if we look at a generic idea of what's going on here, reactants can be taken apart into atomic form. So you have to absorb a certain amount of energy to break all the bonds and form atoms. From those atoms, the atoms combine together making bonds and releasing a certain amount of energy to form substances. So going from reactant to product, we can theoretically go from reactant up to all component atoms, and then from those component atoms down to the products. The overall energy difference between reactant and product is the heat of reaction overall, which is represented by the large solid red arrow. The energy to break the bond would be the blue arrow, and the energy to released in all the bond formation would be the smaller, or the thinner rather, red arrow. So looking at the reaction above, we can represent it in this way. If I have H2 and Br2, we have two molecules here, one that is two hydrogens and one that is two bromines. The energy that must be input into the hydrogen bond to break it is 436 kilojoules. So if I input 436 kilojoules, I'll reach a point where I now have two separate hydrogen atoms, and then I still have the bromine molecule. I have to input 193 kilojoules of energy to break the bromine-bromine bond. If I do that, I've now reached a point where I have the two hydrogen atoms and the two bromine atoms split, where my overall energy is a combination of the 436 kilojoules and the 193 kilojoules. To go from that atomic configuration down to a product configuration, I have to make bonds between the hydrogen and the bromine. There would be two bonds times the hydrogen atom, which would release a total of negative 732 kilojoules. So overall, we're adding 436 and 193 and then releasing negative 732. This gives us a net difference of negative 103, which is the heat of reaction going straight from H2 plus Br2 to the 2HBr. We can calculate a heat of reaction from bond energies in a similar way to we do with Hess's law, like we're doing with the heat of formation earlier. In this case, the heat of reaction is going to be the coefficient of the number of bonds times the bond energy for the reactants as a sum of all of the reactants minus the coefficient of the number of bonds times the bond energy for the products as a sum of all the products. Now here we have reactant minus product rather than the standard product minus reactant we've seen. This is because bond energies are always positive values because we're breaking the bond. So the heat of the reaction is then the energy that's required to break the reactant bonds minus the energy that is required to break all the product bonds. This applies only to the gas state. If there are other phases involved, we need additional thermodynamic data. For instance, if I have to go from a liquid to the gas phase, I would need to know the heat of vaporization of that liquid. This kind of process is going to be less accurate than using a standard heat of formation, but it is useful in times when calculating something by heat of formation is difficult. The only thing that we need to worry about, though, in this kind of a process is the bonds that are changing. If there are any parts of the molecule that are left untouched in the course of the reaction, we can ignore that. So we're only concerned with the parts of the reactant that are changing, the parts of the product that are changing. As an example of this, looking at the Hess's law concept using this equation, if I want to estimate the heat of reaction at 298 Kelvin for the process here where I take nitrogen and hydrogen and combine them to make ammonia, the bonding energy of a nitrogen-nitrogen bond is 945 kilojoules per mole of bonds. For hydrogen-hydrogen, it's 436, and for nitrogen-hydrogen, it's 361. The heat of reaction is going to be the bond energy of the nitrogen-nitrogen bond plus the 3 bonds for the hydrogen-hydrogen. There's one nitrogen-nitrogen bond in the molecule, which happens to be a triple bond, and there are one hydrogen bond per hydrogen molecule. Well, there are 3 hydrogen molecules in the equation, therefore there are 3 hydrogen-hydrogen bonds. On the product side, their ammonia has an NH bond, and each ammonia molecule has 3 NH bonds. Since there are 2 ammonia molecules, there are a total of 6 NH bonds, and so from the reactant in bonding energies, we would subtract 6 times the bonding energy of the NH bond. This means that we have 945 plus 3 times 436, and then subtracting from that 6 times 361, which gives us a net difference of negative 93 kilojoules per mole reaction.